What if everything you've ever seen in the universe is only a small fraction of what's truly there? Not hidden behind distance or darkness, but hidden in plain sight, woven into the very fabric of reality in ways astrophysics is only just beginning to uncover. Tonight, we're going to drift gently into one of the quietest and most profound mysteries ever explored. The idea that the universe we observe is not the universe that exists. That the stars, galaxies, and glowing clouds of light are only faint signals, hints of something far deeper, far stranger, and almost entirely invisible. Because in astrophysics, we don't touch the universe. We don't travel across it. We don't interact with it directly. We listen through faint light stretched across billions of years, through subtle distortions in space itself, through patterns that seem almost too delicate to notice. And somehow, from those whispers, we've built an entire understanding of existence. If you've ever watched our Valoran episode on dark matter, you may remember how galaxies behave as if something unseen is guiding them. Tonight, we'll go even deeper than that, into the foundations of astrophysics itself. Because the deeper you go, the stranger it becomes. Before we begin, take a moment to gently support the channel. Subscribe if you enjoy these quiet cosmic journeys. Leave a like, and consider turning on the bell so you don't miss future explorations. You can also join as a member if you'd like to support even more. And as always, tell me softly in the comments, where in the world are you listening from tonight? Now, let's begin. In astrophysics, everything begins with a quiet limitation, a boundary so fundamental that it shapes every discovery we have ever made. We do not travel to the stars, we do not touch distant galaxies, and we cannot collect samples from the vast structures that stretch across the universe. Instead, we rely entirely on something far more delicate: light. Every piece of knowledge we hold about the cosmos has arrived in the form of light, or more precisely, electromagnetic signals that have traveled unimaginable distances. Some of this light began its journey before Earth even existed, drifting silently through expanding space, carrying with it fragments of ancient events. And when it finally reaches us, after billions of years, it arrives as a faint whisper, a trace that must be carefully interpreted. This creates a quiet but powerful question that sits at the heart of astrophysics. If everything we know comes from light, then what happens when something does not produce light at all? To begin understanding this, we first need to gently expand what we mean by light. The light we see with our eyes is only a very small part of a much larger spectrum. Beyond the familiar glow of stars lies a hidden range of signals, radio waves stretching across vast distances, infrared warmth revealing cold cosmic dust, ultraviolet flashes marking energetic processes, and even X-rays and gamma rays that emerge from the most extreme environments in the universe. Each type of light tells a slightly different story. Radio waves can reveal enormous clouds of gas quietly drifting through space, waiting for gravity to gather them into new stars. Infrared light allows us to see through thick curtains of cosmic dust, uncovering regions where stars are quietly being born. Higher energy light, like X-rays, exposes violent regions near black holes, where matter is heated to extraordinary temperatures. So even before we begin exploring the deeper mysteries, we are already faced with a layered reality. The universe does not reveal itself all at once. It reveals itself in fragments depending on how we choose to look. And yet, even with all these different windows, there is still a limitation that cannot be escaped. All of these observations depend on something being visible in some form. Something must emit, reflect, or interact with light in order for us to detect it. This is where the first quiet tension begins to form, because when astronomers started carefully studying the motion of galaxies, something unexpected appeared. The light we could see, the stars, the glowing gas, the luminous structures, did not seem to account for the behavior we were observing. Galaxies were rotating in a way that suggested there was far more present than what we could detect. But for now, we will let that mystery rest gently in the background. Instead, imagine what it truly means to rely on light as your only source of information. Every telescope, no matter how advanced, is essentially a collector of faint signals. It gathers photons, tiny packets of energy, and converts them into patterns that we can analyze. These patterns become images, spectra, and data, but at their core, they are still just interpretations of light. And interpretation is never perfect. As light travels across the universe, it is altered. It can be stretched by the expansion of space, shifting its color toward the red. It can be absorbed by clouds of gas, leaving behind gaps in its signal. It can be bent by gravity, changing its path in subtle ways. By the time it reaches us, it is no longer a pure message. It is a transformed one. Astrophysics, then, is not just the study of the universe. It is the study of messages that have been distorted by time, distance, and the very structure of reality itself. And yet, from these imperfect signals, we have managed to reconstruct entire cosmic histories. We have traced the life cycles of stars, mapped the structure of galaxies, and even begun to understand how the universe itself evolves. It is a remarkable achievement, but also a fragile one, because it depends on a single assumption that light tells us everything we need to know. But what if it doesn't? What if there are aspects of the universe that do not interact with light in any meaningful way? What if entire structures exist, influencing everything around them, while remaining completely invisible to our instruments? This idea may feel distant at first, almost abstract. But as we move deeper into this journey, we will begin to see that this is not just a possibility. It is something astrophysics is already quietly confronting. For now, though, allow your thoughts to drift gently with this idea that every star you see, every galaxy ever observed, every glowing point in the night sky is not the full picture. It is only the part of the universe that chooses to shine. And in the vast silence beyond that light, something else may be waiting. If light is the only language the universe uses to speak to us, then spectra are the subtle grammar hidden within that language. They are the quiet patterns inside light that transform a simple glow into something far more meaningful, almost like a fingerprint left behind by distant cosmic objects. At first glance, starlight appears soft and continuous, A gentle wash of brightness spread across the darkness. But when that light is carefully separated, stretched out into its individual colors, something remarkable begins to appear. Instead of a smooth gradient, we find interruptions, thin dark lines, bright streaks, delicate gaps that seem almost too precise to be random. These lines are not imperfections. They are messages. Each one corresponds to a very specific interaction between light and matter. Atoms, the smallest building blocks of everything we know, do not absorb or emit light in arbitrary ways. They follow strict rules, allowing only certain energies to be exchanged. When light passes through or emerges from these atoms, it carries those rules with it, encoded as patterns within the spectrum. So when astrophysicists observe a distant star, they are not simply seeing its light. They are reading its internal structure, its composition, and even its history, all from these faint spectral signatures. A single dark line in a spectrum might reveal the presence of hydrogen, quietly absorbing a specific wavelength of light. Another might indicate helium or calcium or iron. Together, these lines form a kind of cosmic barcode, one that allows us to identify what a star is made of without ever touching it. But the story does not end with composition. As we look more closely, the spectrum begins to reveal deeper layers of meaning. The intensity of different colors can hint at temperature, telling us whether a star burns with a cool reddish glow or a hotter blue-white intensity. Subtle shifts in the positions of spectral lines can indicate motion, revealing whether an object is moving toward us or drifting away into the depths of space. And here, the earlier mystery begins to gently resurface. Because when scientists began measuring these spectral shifts across entire galaxies, they noticed something strange. The outer regions of galaxies were moving in ways that did not match the visible matter. The spectral lines told a story of motion, but that story did not align with what we could see. Again, we will let that question linger, just beneath the surface. For now, remain with the quiet elegance of spectra themselves. There are three main ways these patterns appear, and each one tells a slightly different story. A continuous spectrum is smooth and unbroken, often produced by dense, hot objects like stars. It represents a full range of energies, a steady emission of light across many wavelengths. An emission spectrum, on the other hand, appears as bright lines against darkness. It is created when atoms release energy, sending out light at very specific wavelengths. These glowing lines can reveal regions of hot gas, energized by nearby stars or violent cosmic events. Then there is the absorption spectrum, perhaps the most subtle of all. Here, dark lines cut across a continuous background, marking the wavelengths that have been removed as light passes through cooler gas. It is this type of spectrum that often allows us to detect elements in a star's outer layers or in the space between stars. So even in something as simple as light, there are layers of interaction, layers of meaning that must be carefully unraveled. And yet, there is a quiet limitation hidden within this method. Spectroscopy only works because light interacts with matter. The patterns we observe depend on atoms absorbing and emitting energy in predictable ways. But what if there are forms of matter that do not interact with light at all? matter that leaves no spectral lines, no fingerprints, no trace within the very system we rely on to understand the universe. This question begins to deepen the mystery in a subtle but important way, because spectra, for all their precision, only reveal what is willing to be revealed. They are incredibly powerful, but they are not universal. They cannot show us what refuses to participate in the exchange of light. And this brings us back to the earlier tension, the one quietly forming between what we observe and what must exist. Imagine standing in a dark room, illuminated only by a narrow beam of light. Everything within that beam becomes visible, detailed, understandable. But beyond it, in the surrounding darkness, there may be objects, structures, even entire systems, completely unseen, yet still present. Astrophysics, in many ways, operates within that beam. Spectra sharpen our vision within the light, allowing us to read its hidden messages with incredible accuracy. But they also remind us, gently and persistently, that our view is incomplete. Because if something does not leave a spectral trace, it remains invisible to one of our most powerful tools. And as we continue this journey, that absence, that silence in the data, will begin to matter more than anything we can see. There is a quiet shift that happens when we stop looking at light as color and begin to listen to it as motion. Because hidden within the delicate patterns of spectra is not only information about what something is made of, but also how it moves through the vast stillness of space. This discovery begins with a simple idea, one that feels almost familiar. When something moves toward you, the waves it produces become slightly compressed. When it moves away, those waves stretch out. You may have noticed this with sound, the changing pitch of a passing vehicle, rising as it approaches, then falling as it drifts away. Light behaves in a similar way, though far more subtly. When a star or galaxy moves toward us, the light it emits is shifted slightly toward shorter wavelengths, toward the blue end of the spectrum. When it moves away, that light is stretched toward longer wavelengths, toward the red. This gentle shifting is known as the Doppler effect, and in astrophysics, it becomes one of the most powerful tools for understanding motion across unimaginable distances. At first, this effect was used to study individual stars. By observing tiny changes in their spectral lines, astronomers could determine whether a star was moving closer or farther away. Over time, this allowed them to map the motion of stars within our galaxy, revealing patterns of rotation and structure that were otherwise invisible. But as telescopes grew more powerful and observations reached farther into the universe, something far more profound began to emerge. When scientists looked at distant galaxies, they found that almost all of them showed a shift toward the red. Not just a few, not just those in certain regions, but nearly every galaxy beyond our local neighborhood appeared to be moving away from us. At first, this might seem like a coincidence, but the pattern was too consistent, too universal. The farther away a galaxy was, the more its light had been stretched. It was as if space itself was expanding, carrying galaxies along with it, gently pulling them apart over time. This realization reshaped astrophysics in a quiet but profound way, because it suggested that the universe is not static. It is not fixed or unchanging. It is dynamic, evolving, slowly unfolding across billions of years. The light we observe is not just telling us where things are, but when they were. The farther we look, the further back in time we see. And yet, even within this expanding universe, there are smaller, more subtle motions taking place. Stars orbit the centers of galaxies. Gas clouds drift and collapse. Entire galaxies rotate, their arms sweeping slowly through space in vast, graceful arcs. These motions, too, are encoded in light, hidden within the tiny shifts of spectral lines. And this is where the earlier mystery begins to return more clearly now. When astronomers measured how stars move within galaxies, they expected to see a familiar pattern. Just as planets in a solar system move more slowly the farther they are from the center, stars at the edges of a galaxy should orbit more slowly than those near the core. But that is not what they found. Instead, stars far from the center were moving just as quickly as those closer in. The spectral shifts revealed velocities that did not decrease with distance as expected. It was as if something unseen was holding the galaxy together, providing additional gravitational pull that could not be accounted for by the visible matter alone. This was not a small discrepancy. It was a fundamental contradiction. The light told one story, but the motion told another. And since motion is governed by gravity, this meant that either our understanding of gravity was incomplete, or there was more matter present than we could see. This is the moment where astrophysics begins to step beyond observation and into deeper uncertainty. Because everything we have discussed so far, light, spectra, motion, all depend on what is visible. But here, the visible universe begins to fail as a complete explanation. The behavior of galaxies suggests that something else is influencing them, something that does not emit light, does not absorb it, and leaves no spectral signature behind. And yet, it is undeniably present. You can almost imagine it as a hidden structure, an invisible framework surrounding galaxies, guiding their motion in silence. We cannot see it directly, but we can feel its influence through the way stars move, through the way galaxies rotate, through the way light itself bends as it passes through space. This idea introduces a new kind of observation, one that does not rely on seeing something directly, but on noticing its effects. It is a shift from observing light to observing absence, from reading what is present to questioning what is missing. And as this realization deepens, it begins to reshape the entire foundation of astrophysics. Because if a large portion of the universe does not interact with light, then our most trusted tool becomes incomplete. We are no longer just interpreting faint signals. We are trying to understand a reality where the majority of what exists may never reveal itself in the ways we expect. So as you rest with this thought, let it settle gently, that the motion of galaxies, the slow turning of stars, the stretching of light across space, is quietly pointing towards something unseen, something that does not shine, something that does not speak in light, and yet something that may shape the universe more than anything we can see. There is something quietly unsettling about relying entirely on light to understand a universe that may not be fully made of light. Up to this point, everything we've explored has followed a kind of logic. Light travels, we detect it, we interpret it, and from that we build our understanding of reality. But now, as we move deeper, that logic begins to soften at the edges, revealing subtle gaps that are easy to overlook at first. Because light, for all its usefulness, is selective. It does not reveal everything equally. It favors certain environments, certain conditions, certain interactions. Bright stars dominate our view, while faint structures fade into the background. Dense clouds can obscure entire regions, hiding what lies behind them. Even entire galaxies can remain unseen if their light is too weak or too stretched by distance. So what we observe is not necessarily a complete picture. It is a filtered one. Imagine standing beneath a night sky filled with stars. To your eyes, it may seem rich and complete, a vast ocean of light scattered across darkness. But even in that moment, most of what exists above you is invisible. Not because it is too far away, but because it simply does not emit light in a way you can detect. Astrophysics attempts to overcome this limitation by expanding its vision beyond human perception. Telescopes capture wavelengths we cannot see. Detectors measure signals too faint for our senses, and advanced instruments filter out noise to reveal hidden structures. But even with all of this technology, the limitation remains. We are still only seeing what interacts with light. And this becomes especially important when we consider how light behaves over long distances. As light travels through the universe, it does not move through empty, untouched space. It passes through regions filled with gas, dust, and fields of gravity that subtly alter its path. Some wavelengths are absorbed, leaving gaps in the signal. Others are scattered, diffusing the information they carry. In some cases, light is bent, redirected by massive objects in a process so gentle that it is almost imperceptible unless carefully measured. By the time light reaches us, it has been shaped by everything it has encountered. This means that every observation we make is not just a direct view, but a reconstruction, a careful interpretation of signals that have been modified along the way. Astrophysicists must account for these distortions, separating what belongs to the source from what has been introduced during the journey. And even then, uncertainty remains, because not all distortions are easy to detect. Some are so subtle that they blend seamlessly into the data, quietly influencing conclusions without being noticed. Others may mimic entirely different phenomena, leading to interpretations that feel correct but are incomplete. In this way, light can sometimes mislead us, not intentionally, but simply by the nature of how it travels. This creates a quiet tension within astrophysics. On one hand, light is incredibly reliable. Its behavior is governed by well-understood principles, and its interactions with matter follow consistent patterns. On the other hand, those same interactions introduce layers of complexity that must be carefully unraveled. So every image of a galaxy, every spectrum of a star, every measurement of motion carries with it a hidden question. What are we not seeing? This question becomes even more significant when we consider the vast scales involved. Light from distant galaxies may have traveled for billions of years before reaching us. During that time, the universe itself has changed. Space has expanded, structures have evolved, and the conditions that originally produced that light may no longer exist. So when we observe a distant object, we are not seeing it as it is now. We are seeing it as it was long ago. This introduces another layer of complexity, because now, not only are we interpreting altered signals, but we are also reconstructing events from the distant past. Astrophysics becomes a kind of time archaeology, piecing together fragments of ancient light to understand processes that may no longer be directly observable. And yet, even with all these challenges, the field has achieved extraordinary insights. We have mapped the large-scale structure of the universe, traced the evolution of stars, and uncovered patterns that stretch across billions of light years. But beneath all of this progress, the earlier mystery continues to grow, because despite the clarity of our methods, there are still observations that do not fully align with what we can see. Motions that suggest more mass than is visible. Structures that appear to be shaped by something unseen. Patterns that hint at influences beyond the reach of light. It is as if the universe is revealing itself in layers, offering clarity in some places, while withholding it in others. And this brings us gently to a turning point. Up to now, we have relied on light to guide us. We have trusted its messages, refined our tools, and expanded our vision across the electromagnetic spectrum. But the deeper we look, the more we begin to realize that light may not be enough. Not because it is flawed, but because it is incomplete. There may be aspects of the universe that do not interact with light at all. No emission, no absorption, no reflection. Completely silent within the very system we depend on. And if that is true, then the most important parts of the universe may be the ones we cannot see. So as we continue, let that thought settle softly, that even with all our instruments, all our knowledge, all our careful interpretations, we may still be observing only a fraction of what truly exists. And beyond that fraction, beyond the reach of light, something vast and unseen may be quietly shaping everything we know. As we slowly reach the edge of what light can reveal, there is a subtle shift in perspective that begins to take hold. Up until now, we have been following a familiar path, observing light, decoding its patterns, and using those patterns to build a picture of the universe. It is a process that feels stable, almost comforting in its logic. But here, at this boundary, that comfort begins to soften into something quieter, something more uncertain. Because what we are starting to realize is not just that light has limits, but that those limits may define the very edges of our understanding. Everything we have discussed so far, spectra, motion, temperature, composition, exists within a framework where light interacts with matter. These tools work beautifully when that interaction is present. They allow us to reconstruct stars, trace galaxies, and even map the expansion of the universe itself. But when that interaction disappears, so does our ability to see. And this is where the deeper question begins to emerge, almost gently. What if the universe is not designed to be fully observed? Not hidden deliberately, not concealed with intention, but simply structured in a way where some parts do not participate in the exchange of light. parts that exist, that exert influence, that shape everything around them, yet remain completely silent in the one language we rely on. This idea does not arrive all at once. It builds slowly, through small inconsistencies, subtle mismatches between observation and expectation. The motion of galaxies that does not align with visible matter. The bending of light that suggests more mass than we can account for. The large-scale structure of the universe forming in ways that seem to require something unseen. Each of these observations on its own might be dismissed as an anomaly, but together they begin to form a pattern, a quiet, persistent indication that something is missing. And yet, what is missing cannot be detected directly. There are no spectral lines to identify it, no glow to measure, no wavelength to capture. It does not absorb light, it does not emit light, and it does not reflect light in any meaningful way. It exists entirely outside the system we use to observe the cosmos. This forces astrophysics into a new kind of reasoning. Instead of asking, "What do we see?" the question becomes, "What must be there for this to make sense?" It is a shift from observation to inference, from direct detection to careful deduction. Imagine watching the surface of a calm lake. You see ripples forming, patterns spreading outward, disturbances that suggest something moving beneath the surface. But no matter how closely you look, you cannot see the source itself. You only see its effects. In many ways, this is where astrophysics now stands. We see the ripples. We measure the distortions. We track the motion. But the source remains hidden. And this hidden presence is not small. It is not a minor correction or a subtle detail. It appears to dominate the behavior of entire galaxies, shaping their structure and influencing their evolution over billions of years. It acts as a kind of invisible framework, holding things together where visible matter alone would not be enough. This realization carries a quiet weight, because it suggests that the universe we perceive, the glowing stars, the luminous galaxies, the vast clouds of gas, is only a thin layer, a visible surface resting on top of something far more substantial, something we cannot directly access. And so, the role of astrophysics begins to change. It is no longer just about observing what shines. It becomes about understanding what does not, about learning to read the absence of light as carefully as we read its presence, about accepting that some of the most important components of reality may never reveal themselves in the ways we expect. This does not diminish the beauty of what we can see. If anything, it deepens it, because every point of light in the sky becomes part of a larger, more mysterious structure. Every galaxy becomes not just a collection of stars, but a visible trace of something much greater. Every observation becomes a doorway, not just into what is known, but into what remains hidden. And as we gently move forward into the next part of this journey, we will begin to explore this unseen side of the universe more directly. We will look at the evidence, the reasoning, and the quiet conclusions that have led astrophysicists to accept that most of the universe may be invisible, that the majority of its mass, and perhaps even its energy, exists beyond the reach of light. For now, though, let this idea settle slowly, that everything we have explored so far, all the beauty of spectra, all the elegance of motion, all the delicate messages carried by light, may only be the beginning, a surface, a whisper, and beyond that whisper, the true structure of the universe may be waiting, silent and unseen, shaping everything from the shadows. If you're still here, gently listening as the ideas drift deeper into the night, leave a quiet 1 in the comments. There is a moment in astrophysics where observation quietly gives way to realization. Not a sudden breakthrough, not a dramatic discovery, but a slow and steady accumulation of evidence that begins to point in a single, unavoidable direction. It is the moment when scientists begin to accept that something vast, something fundamental, exists beyond the reach of light. This is where we begin to step into what is often called the invisible universe. At first, the idea feels almost abstract. After all, how can something be studied if it cannot be seen? How can something be measured if it leaves no direct trace? But as we carry forward everything we explored in the previous part, the transition begins to feel natural, because the clues have already been quietly introduced. The motion of galaxies that does not match visible matter. The bending of light that suggests hidden mass. The structure of the cosmos forming in ways that require more than what we can detect. These are not isolated puzzles. They are pieces of a larger pattern. And that pattern leads to a single, profound conclusion: most of the universe may be invisible. This invisible component is known as dark matter, though the name itself is more of a placeholder than an explanation. It does not describe what it is, only what it is not. It is not luminous, not detectable through light, not part of the ordinary matter that forms stars, planets, or living beings. And yet, it appears to be everywhere. To understand how this realization emerged, we can return gently to the earlier mystery of galaxy rotation. When astronomers measure how stars move within a galaxy, they use the Doppler shifts of light to determine their speeds. These measurements are precise, consistent, and reliable. They tell us exactly how fast different parts of a galaxy are rotating. Based on what we can see, the distribution of stars, gas, and dust, there is a clear expectation. The inner regions, where most of the visible mass is concentrated, should rotate more quickly. As you move outward, away from the center, the gravitational pull should weaken, and the rotation speed should decrease. But that is not what the universe shows us. Instead, the outer regions of galaxies rotate almost as quickly as the inner ones. The speed does not drop off as expected. It remains strangely constant, as if there is additional mass extending far beyond the visible edge of the galaxy. This is not a small discrepancy that can be ignored. It is a fundamental mismatch between observation and prediction. And the simplest explanation is that there is more matter present than we can see. Imagine a galaxy not as a flat, glowing disk of stars, but as something embedded within a much larger, invisible structure. A kind of halo that surrounds it, extending far beyond its visible boundaries. This halo does not emit light, does not interact with electromagnetic radiation, but it exerts gravity just the same. It pulls, it shapes motion, it holds galaxies together. and without it, galaxies as we observe them simply could not exist in their current form. This idea was not immediately accepted. It required careful verification, repeated observations, and the gradual elimination of alternative explanations. Could our understanding of gravity be incomplete? Could there be errors in measurement? Could unseen ordinary matter account for the discrepancy? One by one, these possibilities were examined and set aside. The evidence continued to point in the same direction. There is more mass in the universe than we can detect through light, and this mass behaves in a way that is consistent across different galaxies, different environments, and different scales. It is not random or isolated. It is structured, pervasive, and deeply integrated into the fabric of the cosmos. But even as this conclusion became more widely accepted, a deeper mystery remained. What is dark matter actually made of? This question has no clear answer. It is not composed of atoms like ordinary matter. It does not interact with electromagnetic forces in the way we expect. It does not form stars, does not emit radiation, and does not reveal itself through spectra. It exists almost entirely through its gravitational influence. And so, astrophysics enters a new phase, a phase where the goal is not just to observe what is visible, but to understand what is hidden, to develop new methods, new experiments, and new theories that can probe something that does not announce its presence in the usual ways. In a sense, it becomes a kind of quiet detective work, following clues, tracing effects, building a picture from absence rather than presence. And as we continue deeper into this invisible landscape, we will begin to see that dark matter is not just a small addition to the universe. It is not a minor correction or a subtle detail. It appears to outweigh everything we can see: the stars, the galaxies, the glowing structures that fill the night sky may only account for a small fraction of what truly exists. So as this idea settles, let it do so gently, that the universe is not just vast in size, but vast in what it hides, and that everything we have ever observed with light may only be the visible surface of something far deeper, far quieter, and far more mysterious than we ever imagined. As the idea of dark matter begins to settle, it brings with it a quiet shift in how we think about observation itself. Because if something cannot be seen directly, then understanding it requires a different kind of vision, one that does not rely on light, but on the way light is affected. This is where one of the most subtle and beautiful tools in astrophysics comes into focus: gravitational lensing. At first, the concept feels almost delicate. Light, which we often imagine traveling in straight lines across the emptiness of space, does not always follow a simple path. When it passes near a massive object, its trajectory bends slightly, curving under the influence of gravity. This effect is not dramatic in most cases. It does not twist light into sharp angles or sudden turns. Instead, it gently redirects it, like a slow current guiding something drifting across water. This bending happens because gravity is not just a force pulling objects together. It is a shaping of space itself. Massive objects create a kind of curvature in the fabric through which light travels. And as light follows that curvature, its path appears altered to us. In everyday experience, this effect is far too small to notice. But on cosmic scales, where galaxies and clusters of galaxies carry enormous mass, the bending becomes measurable and incredibly useful. Because when light from a distant galaxy passes near a massive object on its way to Earth, it can be distorted in very specific ways. The image may appear stretched, magnified, or even duplicated. Sometimes it forms faint arcs around the foreground object, like soft rings of light suspended in space. These distortions are not random. They follow precise patterns determined by the distribution of mass that caused them. And this is where the deeper insight emerges. By studying how light is bent, astrophysicists can map the mass responsible for that bending, even if that mass cannot be seen. Imagine once again that calm lake, where ripples reveal something moving beneath the surface. Gravitational lensing is like watching those ripples in extraordinary detail. By analyzing their shape, their strength, and their spread, we can begin to reconstruct what lies hidden below. And when scientists began applying this method to galaxies and clusters, the results were both clear and unsettling. The amount of visible matter, stars, gas, dust, was not enough to produce the observed lensing effects. The distortions in light were stronger, more extensive, more structured than what visible mass alone could explain. Once again, the same conclusion appeared. There is more here than we can see, and perhaps even more intriguingly, the distribution of this unseen mass could be mapped. Not directly, not through light itself, but through the way it bends light from other sources. These maps revealed vast halos surrounding galaxies, extending far beyond their visible edges. They showed clusters of galaxies embedded within enormous, invisible structures, connected by filaments that stretch across the cosmos. It was as if the visible universe was only tracing the outlines of a much larger, hidden framework. This framework appears to guide the formation of cosmic structures. Galaxies do not form randomly. They gather along these invisible filaments, clustering in regions where the unseen mass is densest. Over billions of years, this hidden structure has shaped the large-scale architecture of the universe. So now, the earlier mystery deepens into something more concrete. Dark matter is not just an idea. It is not just a theoretical solution to a mathematical problem. It has a measurable presence not through light, but through its gravitational effects. And yet, despite this growing clarity, a strange contrast remains. We can map where dark matter is. We can measure how much of it exists. We can observe how it influences galaxies and light itself. But we still do not know what it is. It does not behave like ordinary matter. It does not clump into stars or planets. It does not emit radiation or interact with electromagnetic forces in ways we can detect. It moves quietly through the universe, shaping everything while remaining almost completely undetectable. This creates a kind of dual reality. There is the visible universe, filled with light, color, and structure, the part we can observe directly. And then there is the invisible universe, equally structured, equally influential, but known only through its effects. and the two are deeply intertwined. Galaxies form within halos of dark matter. Light from distant objects is shaped by its presence. The motion of stars reflects its gravitational pull. It is not separate from the visible universe. It is the foundation upon which much of it is built. So as we continue, allow this image to form gently in your mind. A universe where what we see is only the surface, where vast invisible structures stretch across space, guiding the formation of everything we observe, where light itself bends around something that never reveals its form, and perhaps most quietly of all, a universe where the majority of its substance exists beyond the reach of sight, known only through the subtle, persistent way it shapes the light that passes through it. As the presence of dark matter becomes more certain, a deeper question begins to unfold, and not just where it is, but how it shaped everything we see today. Because if this invisible component truly dominates the mass of the universe, then its influence must reach far beyond individual galaxies. It must be woven into the very structure of the cosmos itself, guiding its formation from the earliest moments to the vast patterns we observe now. To understand this, we have to gently shift our perspective once again, moving away from individual objects and toward something much larger, the architecture of the universe as a whole. When we observe the distribution of galaxies across immense distances, we do not see randomness. Galaxies are not scattered evenly like grains of sand. Instead, they form intricate patterns, long filaments stretching across space, dense clusters where thousands of galaxies gather, and vast empty regions known as voids where almost nothing exists. This immense structure is often described as the cosmic web, a delicate and complex network that spans billions of light years. And what is most fascinating is that this web appears to be shaped not just by visible matter, but primarily by something we cannot see. In the early universe, shortly after its beginning, matter was distributed almost evenly, with only tiny variations in density. These variations were incredibly small, almost imperceptible, but they carried within them the seeds of everything that would follow. Over time, gravity began to amplify these differences. Regions with slightly more matter pulled in more material, growing denser, while less dense regions became emptier. This gradual process unfolded over billions of years, eventually forming the vast structures we observe today. But here is where dark matter becomes essential. Ordinary matter alone, the kind that interacts with light, would not have been able to form these structures quickly enough. It interacts with radiation, it experiences pressure, and it behaves in ways that slow down the process of collapse. Dark matter, however, does not interact with light in the same way. It does not feel radiation pressure, it does not scatter or absorb energy, and so it was able to begin clumping together much earlier in the universe's history. In a quiet sense, dark matter acted as the scaffolding of the cosmos. It formed the first structures, the invisible framework upon which ordinary matter could later gather. As time passed, gas began to fall into these dark matter halos, cooling and condensing until stars ignited and galaxies were born. What we see today, the luminous structures that fill telescopic images, are like the visible threads woven along an underlying, unseen structure. This realization brings us back to the central idea that has been slowly forming since the beginning of our journey. We are not observing the full universe. We are observing the parts that shine. The cosmic web itself, when mapped through gravitational effects, reveals that most of its mass is not in the galaxies, but in the vast invisible filaments connecting them. These filaments stretch across unimaginable distances, linking clusters together in a network that resembles something organic, almost like the branching of roots or the delicate structure of neurons. And yet, this structure is made primarily of something we cannot directly detect. It is a quiet, humbling thought that the grandest patterns in the universe, the very shape of its large-scale structure, are defined by something we have never seen. And still, the mystery deepens, because even as we understand the role of dark matter in shaping the universe, we are left with a lingering question. Why does it behave the way it does? Why does it form these structures? Why does it interact gravitationally, but remain silent in every other way we can measure? There is a sense, almost subtle but persistent, that we are only seeing part of a larger picture. That dark matter itself may be just one piece of a deeper framework we have yet to fully understand. And this brings us gently to another layer of the mystery. Because while dark matter explains how structures form and hold together, it does not explain everything. There are observations on even larger scales, involving the expansion of the universe itself, that suggest another unseen component is at work. A component not pulling things together, but pushing them apart. For now, we will not step fully into that idea. We will let it rest, just at the edge of awareness, as another quiet question waiting to unfold. Instead, remain here for a moment with the image of the cosmic web. A universe where galaxies are not isolated islands, but nodes in a vast invisible network, where light traces the outlines of something much larger, where everything we see is guided by something we cannot, and perhaps most gently of all, a universe where the true structure of reality is not written in light, but in something far more subtle, far more silent, and far more difficult to understand. As the quiet structure of the universe begins to reveal itself through dark matter, another, even more subtle mystery starts to emerge, one that does not pull things together, but instead seems to gently, persistently push them apart. If dark matter acts as the hidden framework holding galaxies and cosmic structures in place, then this new component appears to be shaping the fate of the universe itself. And unlike dark matter, which reveals its presence through gravity's pull, this force reveals itself through something far more unexpected: acceleration. To understand this, we return to the earlier idea that the universe is expanding. The light from distant galaxies is stretched, shifted toward the red, indicating that space itself is growing larger over time. For a long time, scientists assumed that this expansion, while real, should be slowing down. After all, gravity acts as an attractive force. The combined mass of all matter in the universe, both visible and invisible, should gradually pull everything back together, gently resisting the expansion. It was a reasonable expectation. A universe that began expanding would continue to do so, but at a decreasing rate, like an object thrown upward slowly losing speed under gravity's pull. But when astronomers carefully measured the light from distant stellar explosions, something surprising appeared. These explosions, used as cosmic reference points because of their consistent brightness, allowed scientists to estimate distances across vast regions of space. By comparing how bright these events appeared with how far away they should be, researchers could trace the history of cosmic expansion. And what they found was quietly astonishing. The expansion of the universe is not slowing down. It is accelerating. Galaxies are not just drifting apart. They are moving away from each other faster and faster over time. The fabric of space itself is stretching at an increasing rate, as if something is gently but relentlessly pushing everything outward. This discovery introduced a new and deeply puzzling concept: dark energy. Like dark matter, the name does not explain what it is, only what it appears to do. It represents an unknown form of energy that permeates all of space, exerting a kind of repulsive influence that drives the acceleration of the universe's expansion. Unlike dark matter, which gathers and clumps, dark energy seems to be smooth and uniform, present everywhere, even in the emptiest regions of space. And this difference is important. Dark matter shapes structure, pulls matter together, forming galaxies, clusters, and the cosmic web. Dark energy, in contrast, works against this process on the largest scales. It stretches space, counteracting gravity, and gradually separating galaxies from one another. Together, they create a kind of cosmic balance, a quiet tension between attraction and expansion. But the balance is not equal. Observations suggest that dark energy dominates the universe even more than dark matter does. The visible matter we are familiar with, everything made of atoms, accounts for only a small fraction of the total. Dark matter makes up a much larger portion, but even that is overshadowed by dark energy, which appears to be the largest component of all. This leads to a realization that feels both profound and strangely calming. Most of the universe is not just invisible. It is fundamentally different from anything we experience directly. The matter that forms stars, planets, and living beings is only a small part of a much larger cosmic composition. The rest exists in forms that do not emit light, do not interact in familiar ways, and challenge our understanding of physics itself. And yet, even as we begin to accept this, the deeper questions remain. What is dark energy? Why does it exist? Why does it have this repulsive effect on the expansion of space? Some theories suggest that it may be a property of space itself, an intrinsic energy woven into the fabric of the universe. Others propose that it could be something more dynamic, a field that evolves over time. But no explanation has yet been confirmed, and the true nature of dark energy remains one of the greatest open questions in astrophysics. So now the picture becomes even more layered. We have a universe where visible matter forms the glowing structures we can observe. An invisible mass, dark matter, provides the gravitational framework that shapes those structures. And an even more mysterious energy, dark energy, drives the expansion of space itself. 3 layers, each interacting, each essential, and yet only one directly visible. This brings us back, once again, to the central idea that has been quietly guiding this journey. We are not seeing the whole universe. We are seeing a small, luminous fraction embedded within something far larger and far more complex. And as we approach the final part of this exploration, we will begin to gather these ideas together. We will look at how stars, galaxies, and gravity fit into this broader picture, and how all of these elements combine to tell a deeper story, not just about the universe, but about our place within it. For now, let this realization settle softly, that the universe is expanding into a future shaped by forces we do not yet fully understand, that most of its substance exists beyond the reach of light, and that even as we continue to explore, there may always remain something just beyond our grasp, quietly guiding the evolution of everything we know. As we slowly reach the end of this part of our journey, something subtle begins to settle into place, not as a final answer, but as a quiet understanding, a realization that the universe is not just more vast than we imagined, but more hidden, that what we see, what we measure, what we carefully decode through light and motion, is only a thin surface layer resting on something far deeper. We began with light, the only messenger we have. We followed its patterns, its spectra, its gentle shifts that revealed motion and structure. And through that, we discovered something unexpected, that the visible universe does not behave as it should, that galaxies move in ways that require more mass than we can see, that light bends around structures that remain invisible, that the cosmic web itself is shaped by something silent, something unseen. And then, as if that were not enough, we uncovered another layer, a force not pulling inward, but pushing outward, a quiet expansion that accelerates, stretching space itself and carrying galaxies further apart over time. A presence that does not gather like matter, but instead fills the universe evenly, shaping its future in ways we are only beginning to understand. So now, if we pause and gently gather these ideas together, a new picture begins to form. A universe where the stars and galaxies we see are only a small fraction of what exists, where dark matter forms the hidden framework, guiding the formation of structure, where dark energy drives the expansion, shaping the destiny of the cosmos on the largest scales. And within this picture, something quietly profound emerges. We are observers of a reality that is mostly invisible. Everything familiar to us, every atom, every planet, every star, belongs to a minority component of the universe. The vast majority exists in forms we cannot directly perceive, forms that do not emit light, do not interact in ways we intuitively understand, and yet dominate the behavior of everything around us. This realization does not arrive with drama. It does not feel like a sudden revelation. Instead, it unfolds slowly, almost gently, like a horizon expanding in the distance. Because in a way, it changes how we think about knowledge itself. Astrophysics is no longer just the study of what we can observe. It becomes the study of what must exist, a careful balance between evidence and inference, between what is seen and what is implied. It teaches us to trust not only our observations, but also the patterns that emerge when those observations do not quite align. And perhaps more quietly still, it teaches us humility, because for all the progress we have made, for all the instruments we have built and the theories we have refined, we are still standing at the edge of something much larger than our understanding. We have mapped the visible. We have traced the invisible through its effects. But the true nature of these unseen components remains beyond our grasp. What is dark matter, truly? What is dark energy? Why does the universe take this form instead of another? These questions remain open, not as failures, but as invitations. Invitations to continue exploring, to continue listening, to continue refining our understanding of a universe that does not reveal itself all at once. And yet, even without complete answers, there is something deeply calming in this picture, because it reminds us that mystery is not something to be feared or avoided. It is something that surrounds us, something that gives depth to our existence. The fact that most of the universe is hidden does not diminish its beauty. It enhances it. Every star we see becomes more meaningful, not less. Every galaxy becomes a window into something larger. Every observation becomes a connection between the known and the unknown. So as we prepare to move into the final part of this journey, allow this sense of quiet wonder to settle, that we are part of a universe where most of what exists is unseen, that we are shaped by processes that began long before we could observe them, and that even now, as we look outward into the night sky, we are only glimpsing a small portion of a much deeper reality. In the next part, we will begin to bring everything together. We will return to stars, to galaxies, to gravity, and see how they fit within this hidden framework. And slowly, gently, we will move toward a broader reflection, not just on the universe itself, but on what it means to exist within it. If you're still here, still listening as these ideas drift softly through your thoughts, leave a quiet 2 in the comments. As we begin the final part of this journey, there is a quiet shift in perspective, a gentle return from the vast, unseen structure of the universe back toward the things we can recognize. Stars, galaxies, gravity, the familiar elements of astrophysics. But now, they no longer appear as isolated phenomena. Instead, they feel connected, woven into a deeper framework that we have only just begun to understand. Because everything we see, every star that glows softly in the night sky, exists within that hidden structure we explored before. Stars are not just points of light. They are the visible expression of processes that are guided, shaped, and sometimes even limited by forces we cannot directly observe. To understand this more clearly, we can begin with something simple: the birth of a star. Stars form from vast clouds of gas and dust, drifting quietly through galaxies. Over time, gravity begins to pull parts of these clouds inward, gathering material into denser regions. As the matter collapses, it heats up, becoming brighter, more concentrated, until eventually nuclear fusion ignites at the core. A new star is born, shining steadily for millions or even billions of years. This process feels familiar. It is driven by gravity, by the balance between inward collapse and outward pressure. But what is easy to overlook is that this process does not happen in isolation. The gas clouds themselves are shaped by the larger structure of the galaxy, which in turn is embedded within a halo of dark matter. So even at the level of a single star, the invisible universe is already present. Dark matter does not directly participate in the formation of the star. It does not collide, does not heat up, does not emit light, but its gravitational influence determines where matter gathers, where galaxies form, and therefore where stars can be born. In a quiet, indirect way, it sets the stage for everything that follows. And once a star is formed, its life unfolds according to its mass. Smaller stars burn slowly, living long, steady lives. Larger stars burn intensely, consuming their fuel quickly and ending in dramatic transformations. Some expand into vast red giants, shedding their outer layers into space. Others collapse inward, triggering powerful explosions that scatter heavy elements across their surroundings. These elements, carbon, oxygen, iron, become the building blocks for future stars, planets, and eventually life itself. So the life cycle of stars becomes more than just a process of birth and death. It becomes part of a larger cycle, a continuous transformation of matter across time. And within this cycle, the influence of the invisible remains quietly present. Because the distribution of stars within a galaxy, the rate at which they form, and the environments in which they evolve, all depend on the underlying gravitational structure shaped by dark matter. Without it, galaxies might not hold together. Star formation might proceed differently, or perhaps not at all in the forms we recognize. So even though we cannot see dark matter, its presence is written into the very existence of the stars themselves. And beyond individual stars, this connection becomes even more apparent when we look at galaxies as a whole. Galaxies are not static collections of stars. They are dynamic systems constantly evolving. Stars orbit their centers, gas flows through their structures, and over time, galaxies can merge with one another, reshaping themselves in slow, graceful interactions that unfold over billions of years. These mergers are not chaotic collisions in the way we might imagine. Stars rarely collide directly. Instead, gravity gently rearranges their orbits, stretching and twisting entire galaxies into new forms. Spiral structures can transform into more rounded shapes. New waves of star formation can be triggered as gas is compressed and heated. And once again, behind all of this, the invisible framework remains. Dark matter halos guide the motion of galaxies, influencing how they interact and merge. They provide the gravitational backbone that holds these systems together even as they change over time. Without this hidden structure, the large-scale behavior of galaxies would be very different. So as we step back and look at the universe now, after everything we have explored, a deeper coherence begins to appear. Stars, galaxies, gravity, they are not separate topics. They are layers of a single, interconnected story. A story in which visible matter plays only one role among many. A story in which the unseen shapes the seen, quietly guiding the evolution of everything we can observe. And perhaps most gently of all, a story in which our own existence is part of this same process. Because the elements within us were formed in stars. The stars formed within galaxies. The galaxies formed within a structure shaped by dark matter. And the expansion of the universe itself is guided by dark energy. So even without seeing it, even without fully understanding it, we are connected to the invisible universe in ways that are both subtle and profound. And as we continue, we will begin to slow down, to move from explanation into reflection, and to explore what it means to exist within a universe that is, in many ways, still unknown. As we continue deeper into this quiet reflection, there is a gentle shift from understanding how the universe works to sensing how it unfolds over time. Because everything we have explored so far, stars forming, galaxies evolving, invisible structures shaping motion, does not happen quickly. It happens slowly, across spans of time so vast that they almost dissolve our usual sense of scale. In our everyday lives, change feels immediate. Days pass, seasons shift, years accumulate in ways we can notice and remember. But in astrophysics, time stretches into something much larger. A single star may live for billions of years. A galaxy may take hundreds of millions of years just to complete one slow rotation. Entire cosmic structures evolve so gradually that, from our perspective, they seem almost still. And yet, beneath that stillness, everything is moving. Stars are being born quietly in cold clouds of gas. Others are fading, cooling, or ending their lives in distant explosions. Galaxies are drifting, interacting, and sometimes merging in slow, graceful dances that take place over immense spans of time. And all of this is happening within an expanding universe, where space itself is continuously stretching. There is something deeply calming in this kind of motion. It is not rushed. It is not chaotic in the way we often imagine. It is steady, patient, unfolding according to the same fundamental principles that have guided it from the very beginning. And within this slow unfolding, the role of gravity becomes even more profound. Gravity is not just a force that pulls objects together. It is a kind of quiet organizer shaping the paths that matter takes over time. It governs the orbits of stars within galaxies, the motion of galaxies within clusters, and the formation of structures on the largest scales. It is always present, always working, even when its effects are too gradual to notice in any single moment. But as we now understand, gravity is not acting alone. It is balanced, almost delicately, by the presence of dark energy. While gravity pulls matter inward, gathering it into structures, dark energy gently pushes outward, stretching space and creating distance between those structures. This balance does not remain fixed. Over time, as the universe expands, the influence of dark energy becomes more dominant, slowly altering the overall behavior of the cosmos. So the universe is not just evolving, it is changing the way it evolves. In the distant past, gravity played the leading role, shaping the formation of galaxies and the cosmic web. In the far future, dark energy may take over, gradually separating galaxies until they drift beyond each other's reach. The night sky, as seen from any one point, may slowly empty, leaving fewer and fewer visible galaxies over time. This idea carries a quiet sense of distance, not just in space, but in time, because it reminds us that the universe we observe now is only one moment in a much longer story, a temporary arrangement of matter and energy, shaped by forces that continue to evolve long after our current observations. And yet, within this vast timeline, there is also continuity. The same physical laws apply across all of it. The same interactions between matter and energy, between gravity and expansion, between visible and invisible components. They persist, guiding the universe through its different phases. This continuity creates a kind of connection across time. The light we observe from distant galaxies carries information from billions of years ago, linking us to moments that existed long before Earth formed. The atoms within our bodies were created in ancient stars, connecting us to processes that unfolded across cosmic history. And the structures we see today are the result of countless interactions that have taken place over immense periods of time. So even though we exist in a very small window of this timeline, we are not separate from it. We are part of the same unfolding. And perhaps this is where the deeper reflection begins to emerge. Because when we consider the invisible components of the universe, dark matter and dark energy, it becomes clear that much of this unfolding is guided by forces we do not fully understand. The largest structures, the long-term evolution, even the ultimate fate of the universe, all are influenced by something that remains beyond direct observation. This does not make the universe less meaningful. If anything, it adds a quiet depth to everything we see. Every star becomes a moment in a much longer story. Every galaxy becomes a phase in an ongoing transformation. Every observation becomes a glimpse into a process that extends far beyond our immediate understanding. And as we continue, we will move even further into this reflection, slowing down the pace, allowing the ideas to settle, and gently exploring what it means to exist within a universe that is both deeply connected and largely unknown. As we continue to drift through this quiet understanding of the universe, there is a natural movement that begins to take place, a shift from observing what exists to reflecting on what it means that it exists in this way. Because everything we have explored, the visible stars, the hidden dark matter, the expanding fabric of space, does not just describe a physical system. It reveals a kind of balance, a delicate interplay between forces that shape reality on every scale. And at the center of that balance is gravity, not just as a force, but as a kind of quiet storyteller. Gravity is the reason stars form, gathering gas from the emptiness and compressing it until light ignites. It is the reason galaxies hold together, preventing their stars from drifting away into the darkness. It is the reason planets orbit, moons circle, and structures persist over time. Without gravity, the universe would not organize itself into anything recognizable. It would remain a diffuse, scattered collection of particles, never forming the patterns we now observe. And yet, gravity does not act alone. As we have seen, it works in constant dialogue with other aspects of the universe. With dark matter, which strengthens its reach and extends its influence beyond what we can see. and with dark energy, which quietly opposes it on the largest scales, stretching space and creating distance where gravity would otherwise pull inward. This creates a universe that is not static, not fixed, but dynamic, constantly negotiating between forces that both gather and disperse. And within that negotiation, patterns emerge. Stars gather into galaxies. Galaxies gather into clusters. Clusters connect into the cosmic web. Each layer builds upon the last, forming structures that are both intricate and vast. And yet, if we look closely, these structures are not permanent. They evolve, shift, and eventually change into something new. A star burns its fuel and fades. A galaxy merges with another and transforms. Even the largest structures are slowly altered by the expansion of space. So what we are observing is not just structure, but process, a continuous unfolding. And perhaps what is most striking about this unfolding is how consistent it is. The same fundamental principles apply everywhere. The same interactions between matter and energy, between gravity and expansion, between visible and invisible components, they repeat across scales, creating a kind of quiet harmony throughout the cosmos. This harmony does not mean simplicity. In fact, the universe is incredibly complex. The interactions between its components can produce behaviors that are difficult to predict, patterns that are intricate and subtle. But beneath that complexity, there is a kind of coherence, a sense that everything is connected through shared rules, shared processes. And this brings us gently back to ourselves, because we are not separate from this system. The atoms that make up our bodies were formed in stars, shaped by nuclear processes that unfolded billions of years ago. Those stars existed within galaxies, guided by the gravitational influence of dark matter. And those galaxies themselves are part of a universe whose expansion is driven by dark energy. So when we look outward, when we observe the cosmos, we are not just studying something external. We are tracing the history of the very matter that makes us who we are. There is something quietly profound in that realization, that the same forces shaping distant galaxies are also present, in a different form, within us. That the same laws governing the motion of stars also govern the behavior of matter here on Earth. That there is no true separation between the observer and the observed, only different scales of the same underlying reality. And yet, even with this connection, there remains mystery. Because while we understand many of the processes that shape the visible universe, the deeper layers, the true nature of dark matter, the origin of dark energy, the ultimate structure of reality, remain beyond our current understanding. This does not diminish what we know. Instead, it frames it. It reminds us that knowledge is not a fixed endpoint, but a path, a gradual unfolding, much like the universe itself. Each discovery opens new questions. Each answer reveals new layers of complexity. And the deeper we go, the more we realize how much remains unseen. So as we move toward the final moments of this journey, allow this idea to settle softly, that the universe is not something fully known or fully unknown, but something in between. A place where light reveals some truths, while others remain hidden in silence. A place where structure and mystery coexist, shaping a reality that is both understandable and endlessly deep. And in that balance, there is something quietly beautiful. As we move closer to the end of this journey, something begins to slow, not just the pacing of the story, but the way we hold these ideas in our mind. Because up to now, we have been exploring, connecting, uncovering layer after layer of understanding. But here, the movement becomes softer, more reflective. The focus shifts from explanation to presence. The universe, as we have seen, is not something simple or fully revealed. It is not a clear picture waiting to be observed all at once. Instead, it is something that unfolds gradually, revealing certain aspects while keeping others hidden. Light shows us part of the story. Gravity reveals another. And beyond both, there are elements that remain quiet, influencing everything without ever appearing directly. And perhaps what is most remarkable is that this hidden nature does not make the universe feel distant. It makes it feel deeper. Because when something is only partially known, it invites a different kind of attention. Not the kind that seeks quick answers, but the kind that lingers, that observes patiently, that allows space for uncertainty. Astrophysics, in this sense, becomes more than a scientific pursuit. It becomes a way of listening, not just to what is clear, but to what is subtle, what is incomplete, what is still unfolding. If you imagine the universe as a kind of vast, quiet landscape, then what we have been doing is slowly walking through it. Not rushing, not trying to reach an end, but simply noticing what appears along the way. A star forming in the distance, a galaxy turning slowly in the dark, light traveling across time, carrying with it traces of the past. And now, as we pause within this landscape, there is a gentle awareness that most of it remains unseen. Not hidden in a way that suggests it will eventually be revealed completely, but hidden in a way that may always remain just beyond full understanding. Dark matter, shaping structure without showing itself. Dark energy, guiding expansion without revealing its nature. These are not temporary gaps in knowledge. They may be permanent features of how the universe exists. And there is something strangely peaceful in that, because it suggests that the universe is not a problem to be solved, but a reality to be experienced. A place where knowledge and mystery exist together, each giving meaning to the other. Without mystery, understanding would feel complete and closed. Without understanding, mystery would feel empty. But together, they create something balanced, something that invites both curiosity and calm. So as we sit with this, the earlier questions begin to feel different. What is dark matter? What is dark energy? What lies beyond what we can observe? These questions remain important, but they no longer feel urgent. They become part of a larger process, part of a slow unfolding that does not need to be rushed. Answers may come or they may not, but the act of exploring, of observing, of wondering, continues regardless. And within that continuity, there is a quiet connection. Because the same universe that holds these mysteries is the one we exist within. The same forces shaping galaxies are present, in subtle ways, in the world around us. Gravity holds us to the Earth. Energy flows through every process we experience. The atoms within us carry histories that stretch back to ancient stars. So even as we reflect on the vastness of the cosmos, we are not separate from it. We are part of the same unfolding. And perhaps this is where the deepest sense of calm begins to emerge. Not from fully understanding the universe, but from recognizing our place within it. From seeing that we are connected to something much larger, something that continues whether or not we fully comprehend it. From realizing that mystery is not something outside of us, but something we are already a part of. So as the final segment approaches, allow this awareness to settle gently, that the universe is not just something to observe from a distance, but something we are quietly embedded within, that its hidden layers are not barriers but depth, and that even in the absence of complete understanding, there is still meaning, still connection, still a quiet, steady sense of belonging within the vastness of it all. And now, as everything begins to slow, there is no need to search for new answers, only to rest gently within what we have already uncovered. Because the journey through astrophysics, through light and motion, through the visible and the unseen, does not end with a final conclusion. It fades softly into a wider awareness. The universe does not rush. It does not hurry toward resolution. It unfolds quietly, continuously, without needing to explain itself all at once. And in that unfolding, there is a rhythm. Stars are born in silence, deep within cold clouds that drift through galaxies. They shine for vast stretches of time, steady and patient, before slowly changing, transforming, and eventually fading. Galaxies themselves move with a kind of grace that is almost impossible to notice in a single moment, yet undeniable across millions of years. Even the expansion of the universe, driven by forces we do not fully understand, happens not in bursts, but in a steady, gentle stretching of space itself. Everything moves, but nothing feels rushed. And perhaps that is where the deepest sense of calm begins to settle. Because when we step back from the details, from the questions and the theories, what remains is not confusion, but continuity. A universe that exists, that evolves, that carries forward its patterns whether or not we fully grasp them. A universe where light reveals what it can, and where darkness holds what it does not. And both are part of the same whole. We have seen how light allows us to trace the composition of stars, to measure motion, to look back in time. We have followed those clues into deeper mysteries, discovering that much of the universe does not interact with light at all. That dark matter forms a hidden structure beneath everything we see. That dark energy quietly shapes the future of the cosmos. And yet, even with these mysteries, the universe does not feel incomplete. It feels layered, like something that reveals itself slowly, not because it is withholding, but because it is vast. Too vast to be understood all at once. Too deep to be fully seen from a single perspective. So instead, we experience it in moments. A point of light in the night sky, a faint signal captured by a telescope, a quiet realization that what we see is only part of what exists. And these moments are enough. They do not need to form a complete picture to have meaning. They do not need to resolve every question to feel whole, because the act of observing, of wondering, of gently exploring is already part of the connection we have with the universe. And perhaps this is the final, quiet insight that remains, that we are not separate from the mystery. We are part of it. The same processes that shape distant galaxies have shaped the atoms within us. The same laws that guide the motion of stars also guide the world we experience every day. Even the limits of our understanding, the boundaries of what we can see and know, are part of the same reality we are trying to explore. So when we look into the night sky, we are not just looking outward. We are, in a quiet way, looking back into the deeper structure of existence, a structure we belong to, even if we do not fully understand it. And as this thought settles, there is no need to hold onto it tightly. Let it drift, like light traveling across space. Let it soften, like distant stars fading into the background of the sky. Let it remain as a quiet awareness that does not need to be explained. Because the universe will continue. Stars will continue to form and fade. Galaxies will continue to move and evolve. Space itself will continue to stretch into the unknown. And within all of that, there will always be something unseen, something unresolved, something quietly waiting beyond the edge of understanding, not as something missing, but as something that gives the universe its depth. So as you rest here at the end of this journey, allow everything to become still. There is nothing more to solve, nothing more to reach, only the quiet presence of a universe that exists, vast, layered, and gently unfolding. And somewhere within it, so do you. If you're still here, still drifting through these thoughts as they settle into the calm of the night, leave a quiet 3 in the comments.